Hi, it's Celia. Last semester, I took a course called Data Structures and Algorithms and earned my first B. But wait, it wasn't because the content was difficult to understand. I was struggling because I kept avoiding studying due to it being super unfun, and there were plenty of other distractions I'd rather do instead. In fact, once I had nothing but time on my hands for the final, I forced myself to lock in for 19 torturous hours and managed to score within the top 10 of my class of 111. Honestly, an 80 isn't even that much of a flex, especially in this class where the final was only worth 14% of the grade. But let me be proud of myself, for in those 19 hours of studying, I realized several things. One, my friend who majors in a completely different department let me yap to her about what I was learning for hours on end, and it was actually incredibly effective in helping me clarify my understanding, even if she stayed a silent student with all of my teachings going straight out the other ear. Two, how do these traditional interpretive dance videos simulating various sorting algorithms even exist? Like, who sat down one day and said, you know what merge sort needs? A little choreography and colorful outfits. I think I spent at least an hour down the rabbit hole of this YouTube channel when I was supposed to be studying. But honestly, this counts as studying, right? I mean, if someone asked me to explain quicksort, I'd be like, picture 10 Hungarian guys tap dancing and passing it out on beat. But this is just such a memorable and fun way to learn and remember how these sorting algorithms work. So, why aren't there more fun ways to learn about data structures and algorithms? Well, it doesn't even need to be fun, but anything's better than the generic boring online textbook. The day I took the final exam was also the day I headed home back to California, and I was thinking and planning all the way back. On the train, I was sketching, and on my phone, I was CADing. I already CAD with touchpad on my laptop, so I don't think CAD on phone is too weird, but anyway. By the end of my vacation, I came back to campus ready to throw in the first versions of the 3D print on the school printers. Here are my two shuffleboards. We have this rectangular one for demonstrating various sorts. Just pop in the numbered pieces and slide them around. It's basically a fidget toy for algorithm nerds. Flags on the top can be used as markers depending on the type of sort. This semicircle one is used for demonstrating a binary tree. You simply slide in the nodes from the top or bottom, and then they can be moved around the 7 different positions. It's basically a tiny stage for your data to perform structured drama. Okay, so these 3D printed gadgets provide a tactile way of understanding to reinforce what is taught purely visually. But it's still not fun, you know? Yeah, that's where the board games come in. Okay, so I need your help coming up with names of these games, but the first one has to do with graph theory and minimum spanning trees, and I designed it with Catan as the inspiration. So the setup starts off with randomly placing down these hexagons, kind of like how you'd randomly distribute the resource tiles and dice values in the settlers version, and the sum of the tick marks would be the cost of each road. This is a strictly two-player game, where one represents Prim's algorithm by being forced to buy the next cheapest connected road, while the other represents Kruskal's algorithm by being forced to buy the next cheapest road on the whole map. The goal is to build a connected road between the marked start and end nodes. Prims and Kruskal's are actually the two algorithms for building minimum spanning trees, but the entire map would have to be connected. But we take a bit of creative liberty here and focus on remembering the way these algorithms work. On their turn, the player will start by drawing a card, where it can be either a random die roll for cash or a graph theory related pop quiz for cash. I'm mixing various question types like true or false, short answer, and fill in the pseudocode. There are also 3 cards that call for demonstrating BFS, DFS, and Dijkstra's algorithm. You would roll both dice to choose the start and end nodes, then use the worksheet and paper numbers to work through the graph's nodes. I also designed these 2 additional worksheets for each player to practice keeping track of the rows that they build throughout the game. For the adjacency matrix, when a new road is added, mark the intersection of the 2 nodes with the road's cost. Don't forget the other way too, symmetry matters. For the adjacency list, when a new road is added, the directly connected nodes are updated. Furthermore, we have to update the family index. Think of it like where each node starts off with a unique last name, but when nodes connect, they will share a last name. Usually, the connected nodes will take on the larger family's last name, but for combining equally sized families, the smaller index will be used. I taught my sister how to play, and it's easily fun even while skipping the difficult question cards she couldn't answer. This is proof that the concepts of graph theory are so simple, anyone can just learn them through this game. Now, the second game can be played with 2 or more people, and it's a lot simpler. There are 3 modes, min heap, max heap, or AVL tree. For setup, just grab 5 random nodes and place them on the tree. In min heap, the nodes are organized where the node on top must always be smaller than the nodes beneath it. It's the opposite in max heap. In AVL tree, the nodes are organized where the node to the bottom left is smaller, while the node to the bottom right is larger. On a player's turn, they will first check if there is any reorganization needed for the tree. What this means is for a min or max heap, if any of the nodes are out of place of not being smaller than its children, or larger for max heap. If so, then the player must begin with fixing what is out of place using swims, which is swaps between a node and one of its children. A player can do up to 2 moves per turn, so if there is no more reorganization needed, then they can also use a move by adding a new node from the pile, which would have to go in the bottom row on the farthest left, or removing the node at the top, which involves first swapping with the node on the bottom row farthest right. Once the node has been removed from the tree, it cannot be re-added. And for the AVL tree, adding a new node follows the rules of going left for smaller and right for larger, while instead of only the top node being removable, a player can choose to remove any node in the tree. As for the reorganization, players will have to check if the tree is balanced, which is where the balance factor for each node is between -1 and 1. The balance factor is calculated by the heights of a node's 2 children. For example, this tree isn't balanced because its left child is much taller than its right child, but the height of the right child is -1 since there isn't a child at all. Anyway, the players take turns to make their 1 to 2 moves, and at the end, the last move will be removing the last node off the tree, so whoever is forced to do that move is the loser. This time, I taught both my sister and my mom how to play, and they caught on the swimming and rebalancing rules quickly. The link to the printouts of these board games, as well as the 3D printing files for the physical learning tools, are all in the description. And I'd recommend printing on cardstock for durability, but if you don't have cardstock, even basic black and white printing on regular paper is enough. I hope you have fun with these new hands-on instructional aids in your arsenal. Thank you for watching!